if you take certain metals and you reduce their temperature, there comes a point where they become superconducting, where electricity can pass through them and there's no resistance and they don't get hot and it just moves. We call that superconductivity. In the 1970s and 80s, there was research into, can we make superconducting materials at a higher temperature? In other words, as you lower the temperature of the material, can it become superconducting at a much higher temperature than previously enabled?
Why is that important to seek it at a higher temperature?
Because if you can find a room temperature superconductor, that would transform everything.
Yeah, but then every average person is going to have it, and then we're going to have all these
power.
people with superconducting.
With superpowers.
And then all of a sudden, people are going to be turned into like little ants, like Ant-Man. What are you people, crazy?
Is that how he became an ant?
You guys can't put power like that in a hand.
Okay, that's a very good point.
You want to meet my brother-in-law? You don't want that guy having...
It should have some guardrails, right?
Okay.
So it came of age when higher temperature superconducting materials were becoming available. And why does that matter? For any collider, you're accelerating particles. The particles have an electric charge. And if you move an electric charge through a magnetic field, you can accelerate it.
Okay.
And you adjust the magnetic field, make it just right. It can get very, very fast. The particles can go very, very fast, hitting 99% the speed of light.
What does the manifestation of that very fast-moving particles look like? Is that the electric?
It's just a beam of particles, like typically protons, and you slam it into a target.
Okay.
And that creates a field of energy out of which brand new particles can form.
And we harness that energy for
No,
what?
it's not for energy. It's for what new particles exist in this universe that we didn't know about before we turned on the switch.
Okay, we have enough particles. Why do we need new particles?
Because you always want more particles.
What are you doing with the new particles?
We need more because a new particle might explain something we didn't understand.
Oh, okay. So you're constantly in search of...
Yeah.
Yeah, it's like what we were talking about on another show. So you never...
Probing the
never
universe.
Rest.
Yeah, you never rest. So it came of age at that time. And by the way, it's still the Cold War, early 90s. So under Reagan, we say, yes, let's start this project. Superconducting super collider. They dig the hole. By the way, it would be the largest and most powerful super collider in the world.
You dig a hole somewhere out.
Yeah, it's like, I forgot the diameter, a couple 100 miles. I mean, huge.
Yeah, it's the Meadowlands. That's what they did it.
Some states are not large enough to contain this collider, such as Rhode Island, all right?
This is where I'm from.
You're from Rhode Island.
That's my home state.
You can't...
Can the world stop making any small reference and compare it to Rhode Island? Can we all move on from that? If I hear blankety blank, twice the size of Rhode Island, I'm going to create my own super collider and zap you. Okay,
I didn't know it was that sensitive. Rhode Islanders carry the issues.
Yes. We have size issues.
You have issues.
As it were.
Okay. So Texas clearly big enough. So it's in Waxahachie, Texas. Okay. They acquired the land, started digging the hole, and the years go by. Around 1989, 1990, the government takes another look at the contracting, the budgets, and they judge that there are cost overruns that we cannot afford, and they zero the project. That's different from canceling it, but it's the same thing.
From what I read, the project was fairly far along.
Yes, it was. Yes, it was. The research, the engineering, and then they zeroed the project. And once that happened, the center of mass of particle physics would no longer be in the United States. But just because you don't do it doesn't mean some other folks can't or won't. And the European Center for Nuclear Research, CERN, which is located in Switzerland, but it's a European consortium, an international consortium, I should say, they said, all right, you're not going to do it, we're going to do it. So then they built, as part of their facility, the Large Hadron Collider. You might have heard of that, the LHC. That became the detector that found the mythical Higgs boson, the God particle, the particle whose field grants mass to other particles. That's badass. If you're going to be a particle, that's the particle you want to be.
You want to be.
And so there's a book called The God Particle, written about the Higgs boson. That was written decades ago because we knew that it should be there. We don't have an accelerator that can detect the energies where we would find it.
So, in all seriousness, why couldn't the scientific community in America convince federal government and the people funding this that this was a mistake?
Because they didn't call it a super duper collider. That's my answer.
Those idiots would have understood the significance.
Okay, so what? There is a report that talks about the budget that we can't afford it.
Is there a possible way to generate an artificial magnetic field on Mars so that it can have a thicker atmosphere and protect colonists on the surface from radiation? It's a two-part question.
This is deep.
It's a two-part question.
People thinking all about it.
There a technology that we could theoretically develop, or would we be better off trying to build underground colonies on Mars?
Yeah. So what what she knows is that here on Earth, we have a magnetic field. Not very strong, but we have one. That's why compasses, anybody remember what a compass is?
Yeah, yeah.
Okay.
Old school.
Old school. We have a magnetic field, and when dangerous charged particles come from the sun, we call it the solar wind, they see Earth's magnetic field, and then they channel themselves away and funnel in at the poles, and they collide with our atmosphere and render it aglow, causing the aurora. So when we see the aurora, that's the atmosphere and our magnetic field shielding us from harmful radiation.
Wow.
Okay, so if we lose our magnetic field, the radiation just comes straight in wherever it hits. Mars, we may have once had a magnetic field, it does not any longer. So if you pitch tent, you're susceptible to this flux of high energy particles. So she was correct to wonder, will we just have underground colonies?
Yeah.
All right. And then I'd wonder, well, then what the hell is the point of being on Mars?
But, yeah,
We'll live underground. You live underground here.
We'll be basically the ants of Mars.
The worms, whatever. Like, what's the point of that?
Yeah.
Just consider that almost anything will protect you from those particles, like the roof of a house.
Yeah.
Okay.
Yeah.
So if you could just, the shielding doesn't have to be elaborate. It just has to have some kind of shielding. And there's a whole branch of NASA. Well, there's a branch that studies the sun and a subdivision of it that specializes in space weather. We call it space weather, which is when is the solar wind coming? Because it correlates with explosions on the sun.
Yeah.
It's not just at any time.
Yeah.
So as the sun goes through cycles, it goes through intense periods and then it quiescent. It's an 11-year cycle. So as it pumps up, we get more warnings about explosions on the sun. And as it drifts off, there's fewer. And we know when a pulse of these particles is going to hit us because it takes time to get from the sun to Earth or to Mars. So we just have a warning sign.
Yeah.
Is that any different from saying thunderstorms this afternoon?
Yeah,
4 o'clock,
tornado warning.
Tornado warning, bring an umbrella, but this would be a special solar wind umbrella.
Right, right.
And so I don't see it as an impossible thing to overcome.
That is cool.
And maybe you create some local magnetic field and direct the particles off to the north and south of your little city in a bubble. Whatever. I mean, they could be, engineers figure this stuff out.
I love this.
I'm not worried about it.
that is a wonderful thing to say about the magnetic field. It's protecting us.
It's protecting us.
It's so beautiful.
Oh, yeah.
He says, how far are we away from being able to track gravity waves? I know we can detect them, so tracking them would be the next obvious step, in my humble opinion, that is. If we could track them, eventually we could map the universe edge to edge. Am I correct in thinking that?
So a couple of things. First, a technicality.
Right.
The kind of waves made by
Gravity waves by two colliding black holes.
Okay, those are called gravitational waves.
Gravitational waves, right.
Okay, gravity waves is something else that acoustical people, is a term people use when they refer to a medium that's rising and falling in response to a pressure impulse that goes through it.
Right.
So those are gravity waves that they call. So we have to make sure that the kingdom is separated.
Right.
There, okay. The lexicographic.
Nice. the lexicographic reference has to be correct.
Distinct. So gravitational waves. So
Okay.
We detect them when they wash over us.
Right.
That's what LIGO did. That's what earned the Nobel Prize.
Right.
And do you know who earned the Nobel Prize? Kip Thorne, who was one of the executive producers on
Wait a minute. Wait, it's the string theory movie with Matthew McConaughey. It's called
Interstellar. Yes, good.
Yes.
So in fact, we took our crew out to Pasadena, where he lived, went
Okay.
to his home office,
Wow.
and interviewed Kip Thorne.
Very cool.
Yeah. You can find it on our archives. And he showed us his Nobel Prize.
Oh,
And
wow.
That was cool.
You just keep that thing, huh? You
I know,
just
right?
Keep it
What
around?
what do you do? Wear on your
Yeah,
neck? What do
yeah.
you do? What else do you do with it?
I would take it everywhere.
Oh, yeah.
You know what I mean? Excuse me, do you know what time it is? I'm like, oh, excuse me, let me move my Nobel Prize out of the way so I can see my watch. How did that get there?
Where did that come from?
Oh my goodness, is that my Nobel Prize and where my watch should be? Oh my goodness.
So here's what I learned recently, that yes, we can detect certain energy levels of gravitational waves that wash over Earth.
Right.
And there's certain other phenomena in the universe that do make gravitational waves that those detectors cannot see.
Okay.
Now, there's something I only know a little bit about here, so I just want to put it on the table.
Okay.
That there's a research program that's going to be put into play that wants to detect the effect of gravitational waves moving across across your field of view. So if you have a pulsar, which has very, very precise spinning rates, the most accurate
Set a clock by it.
you can set a clock by it, okay?
Right.
If a gravitational wave passes by it,
Right.
there's a change in the rate.
Right. You'll see the rhythm change.
The rhythm change just briefly.
Yes.
And so the idea is you monitor all the pulsars, you get their
Right.
rhythms known,
Right.
and then you see one change. And then you look to see if it...
If it coincides with a gravitational wave.
Well, that would be the evidence
That
of
would
one.
be the-
Now you
right.
see if it moves to the next one and then the next one.
Oh, right.
At the
And
speed
now
of light.
you would see the consistency across each pulsar.
Correct. And you'd be watching a gravitational wave
move across the medium of space.
Yes.
That's amazing.
Yes.
And
We're not there yet, but that's an idea.
unfortunately, we had to cut that.
Would you stop?
The funding for it's been cut already. We've saved so much money by not even thinking about it. You know it. I know it.
I see a lion and it starts running after me. I'm not going to process all the information in that scene other than that I might die.
Yes.
So, and then I run away or I climb a tree. What information would be distracting to me in that moment?
In that sort of situation, there's a lion running at you and you see a big, blurry, heavy thing fast approaching you. You want to get away. If you're able to survive, you may actually realize, hey, it wasn't a lion. It was actually a tiger. So what?
I could have stayed there and say, I think that's a lion, but maybe it's a tiger.
I'll let it get closer.
I want to make absolutely sure.
Actually, it's not clear what continent that would be on. I don't think they coexist.
No, well-
But they do in The Wizard of Oz. Lions and tigers and bears.
And bears.
So I have the capacity to see the teeth of the lion, count the teeth, make a judgment how white they are. Is it a female lion or a male lion? I could think all of that. Is this the example of things your brain could be doing but is not doing because you have a higher singular priority?
Exactly. And it would be a mistake to want to do these things and to make sure because it's just pointless. And what you care about is just get away as fast as possible.
If you could bend the laws of physics to your will, what would you change, if anything?
Ooh, okay. So in graduate school, there's a calculation you do where you look at the gravitational constant, which was first proposed by Isaac Newton, but it would take centuries later to measure its value reliably. What is the gravitational constant? It's the thing that's in the gravity equation that tells you how to calculate how much gravitational force you get from how much mass. So the force is proportional to the mass. How do you turn that into an equation? You have what's called a proportionality constant, the gravitational constant. You don't know this, but you've been invoking that ever since you recited the equation E equals mc squared. All that equation says is energy is proportional to mass. How do you turn that into an equation? You need a proportionality constant. That's the c squared, the speed of light squared. And so all of these understandings of how the universe works, where you have something on one side of the equation, something on the other, there's a constant there. Constant of proportionality. You make the measurement. Okay, so one of the calculations we do is we take the gravitational constant and say, what happens if we change it by a little bit? What are the consequences to the universe? It turns out that you run the gravitational constant through your equations of a star, and if you change the gravitational constant by a little bit, increase it by a little bit, it has stupendous consequences on the luminosity of stars. The luminosity of a star is dependent on the 7th power of the value of the gravitational constant. So if I double the value of the gravitational constant, it was 2 to the 7th power. 2 times 2 is 4, 8, 16, 32, 64, 128, 2. The luminosity of stars would grow by a factor of 256, thereby reducing their life expectancy. The universe would be much brighter,
Yes.
but they would burn their energy faster, and they wouldn't last long enough for planets around them to evolve into complex life. It would be devastating. That's a lesson to us all. If you want to mess with the universe, you got to be prepared for the consequences.
F around and find out.
Now, that being said, there's a book series called Mr. Tompkins in Wonderland, written by a physicist, George Gamow, a mid-20th century physicist. Brilliant.
Yeah.
Brilliant guy. He first calculated that after the Big Bang, you would have a cosmic microwave background, okay? It made very important calculation. Anyhow, he wrote a series. He wrote for the public, so he's after my own heart here.
All right.
Mr. Tompkins in Wonderland. In each of these books, Mr. Tompkins was in a world where one of the constants of nature was different. So one of them is the speed of light is 60 miles an hour.
Oh, wow.
So he's driving down the street
In the dark.
and he sees phenomenon that you would see only if you went very fast near the speed of light, like in a normal situation. But the speed of light's not 60 miles an hour.
creative is
Very
that?
creative. Yeah. It's beautiful. You know, there's something called dispersion, and it's diffraction, dispersion, refraction. This is what light does as it goes through a hole in the wall or goes around a corner or goes into another medium. If you change the value of Planck's constant, that's the constant for quantum physics, there's a value you can make it so that if you walk through a doorway, you will diffract. It'll affect you macroscopically in the way it previously only affected particles. And so I thought it'd be fun to dial that up just so I can live in the world of quantum physics just for a day.
Now, that'd be cool.
That's what I'm saying. That's all those rules are different.
Yeah,
And
that's a completely...
so I would do that just as an amusement park, not as a thing.
Right.
I'm not messing with the laws of the universe otherwise.
I have always wondered how giant gas clouds and nebula exist in space. Shouldn't the vacuum cause all gas to disperse evenly to the point of not being even being able to see it?
I love that because on Earth, any cloud of gas disperses.
That's right.
As dogs know.
That's right.
Dogs will smell you from far away because whatever's your stank.
Yep.
1 minute in, and he says the guest has stank. This is a lesson, anybody watching, on how not to host a show.
At least it's not smell-o-vision. Goodness
Smell-o-vision.
gracious.
Yeah. So it does dissipate.
It's a great question,
You look
actually.
at blood in the water, and that
But does it dissipate evenly?
it's a diffusion equation
Right.
where you have molecules. It wouldn't happen in solid because all the molecules are just rigid, but in a
They can
fluid.
vibrate. They can vibrate.
No, but you're not going to move it through the system.
No, there's a phase issue.
I'm saying
I know,
it's not going to move through the system.
Just trying to get technical.
Okay,
Yeah.
and
Wow, this is getting tense already.
Well, he called me skank. I mean, what am I supposed to do?
I didn't say skank.
You know
I said
what?
Stank.
Stank.
We don't need this. We'll do our own show.
There we
Come
go.
on,
Okay,
let's
Paul,
go.
we out of here.
No. So the diffusion equation, so you have a molecule that can move like all the others, and it just works its way through. In my high school, there was a diffusion experiment where there's a long tube. It was in one of these display, because we didn't have any athletic trophies to put to a geeky high school. So you got to put other stuff in your hallway display cases.
There's a hall of beakers. Is that right?
Yeah, one of it is a very tall beaker, yes, about this tall, if I remember correctly. I was littler, not much littler, but I think it was this big. And there was ink at the bottom,
Yes.
and they carefully put water on top of it.
Yep.
And throughout the year, you got to watch, because the ink is slightly denser, but still they're both fluids. And so you get to watch the ink work its way up real slowly.
At my high school, they had diffusion experiments every afternoon after the school lunches were served bean soup.
Oh,
And in every classroom, there would be an
was-
experiment of
was-
different particles suspended in the
There was-
atmosphere, moving from one side of the classroom to the other.
I get it.
After you first heard
Right.
that
and
something
people
was
didn't
coming.
figure out to not eat the bean soup.
Right,
okay.
exactly. And that's where you got your name, Skank.
Stank.
So did you? Could you do that same with the ink? Could you do it with oil, like cooking oil?
Yes.
Or olive
Well,
oil? Would it
it's
work?
harder. No, because oil would float, and the miscibility between oil and water is very different because most inks that we use today are water-based anyway. So the water is finding the water molecules.
Yeah. So Brian, the answer is basically the conditions out in space make it so that these gas particles tend to disperse unless they have a reason to collect. Okay. Here on Earth, you have different kinds of things like buoyancy involved and things like that. That also happens in space. But in space, when the temperatures are very low, say 400 degrees below 0 Fahrenheit, gravity can actually overcome a lot of the motional sort of dispersive, diffusive.
Emotional.
Emotional.
Okay.
Yes. It could be emotional. You know,
Clown said, I ain't doing this.
It's very moving.
that's right.
You tear up. You start crying a lot.
Emotional. I never
It's
heard
true.
that word.
About
Okay,
to become
emotional.
a star. Oh my gosh. Yeah.
Yeah, some gas
when it's
stars become
cold,
stars, yeah.
Yeah, when it's cold, the random motions of the gases are actually overcome by the mutual gravity that they exert on each
But
other.
does it happen? Is it dispersing in an even nature?
Not at all.
evenly? No.
Everything is turbulent. If you go see, for example, beautiful pictures of, say, the Orion Nebula or other interstellar clouds cloud, you see that they're streaky and strange and unusual shape. They look like horse heads. They look like helixes and cat's eyes and things like that. And that's completely because the turbulence is still going on.
Is it that,
but
or
just
because
on
you're smoking
gigantic
something
scales.
funny?
That
Is
too.
right?
You know,
Both work.
we got to ask these stars that are emitting their planetary nebulae, what do they smoke? You know, I think that would be a very, very good idea. But the bottom line is that in space, you have gravity holding these clouds together long enough for them to do things like form stars and planets. But there's always these forces and these different energies and so forth for trying to disperse them. And so you get beautiful combinations, and that's why you get beautiful nebulae, and you get things like stars and planets.
I will add that you have a gas cloud that makes a family of stars. So that eats up most of the mass of the gas cloud. But there's part of the gas that didn't participate in the formation of the
little
planet.
snooty, like you were in high school. A little snooty, a little standoffish. Nah, I don't
It just wasn't there. It was, and that gas doesn't always land on a star.
Do we know why? In all seriousness.
Well, now the gas doesn't have enough gravity to make it a next star. We're done.
No, but at the time, and I'm not trying to be
Oh,
funny.
no, it's too far away. So watch
that
it.
gas,
I got this.
like all the other gases, had an equal opportunity
I
to be
got
part
you.
of that.
It's not an equal opportunity system. If you're a little too far away, you might not feel the strong enough gravity to participate. And the stars form without you. I like that hand gesture because I'll follow up on it. The whole galaxy is rotating, okay? So your whole system with your stars and your gas is moving, and there's slew other stuff. So your gas can get stripped and scatter into the galaxy, never to make another star.
So that gas just continues as gas throughout the universe.
And these are the particles that comprise the interstellar medium, even between the gas clouds.
Yeah.
It's not completely empty.
Right. Here on Earth, we have trillions upon trillions of particles of gas, even in the tiniest beaker or vial. But out in space, just even a couple 100 miles above Earth's surface, we're lucky if we even get one gas particle.
It'd be the best vacuum
that
ever
same
created
space.
on Earth.
Yeah.
Is what just space.
So people who study interstellar clouds are literally studying nothing.
Yeah.
And yet that's the nothing from which.
Right. So it's endlessly fascinating.
Yeah.
Such is the layout of this cosmic ballet,
Well said.
choreographed by the forces of gravity.
More like a Martha Graham kind of ballet makes it too orderly.
I don't know. I'm feeling Alvin Ailey.
Okay.
A little Alvin Ailey going
Oh
on.
yeah, we go Alvin Ailey.
All right, okay.
Alvin Ailey
I've been buked.
wins every time. What's the smallest life you could possibly have? Well, we have the viruses, and people like arguing about whether it's really alive, but
They seem alive to me.
But is a molecule alive? I mean, once you're down there, then quantum physics matters.
Right.
Okay? Quantum physics. We don't experience the phenomena of quantum physics as big macroscopic objects. Frankly, neither do insects.
Right.
But
They're too big.
There's a size below which the quantum world would be everything you ever knew or cared about. But we don't have life that small because life has certain complexity that requires some minimum number of molecules in order to declare it life. There's a physicist turned astrobiologist who is thinking about how to quantify the molecular identity of a life form and asking what is the smallest value it can have and still be considered life.
Life, right.
Right. So below that, we think we're not going to find life. That's why. That's why when we discovered the solar system or planets orbit the sun, and then we probed the atom. Oh my gosh! There's
It's a
electron.
little mini solar
It's a little-
system.
It's a little mini solar system.
Right.
So could it be this all the way down?
Right.
In fact, the space occupied by electrons orbit around their atoms uses a word derived from our word orbit. They call it orbitals.
Right.
Okay, because they're not in clean things. They're like in probability of clouds. Okay, where they can occupy any space within there.
Right.
So it's different, but we so wanted it to be the same, just philosophically.
Yes.
But it's not. All the rules are different. Quantum physics overrides Einstein gravity, Newtonian gravity, everything. Do you remember that scene in Men in Black where they had to find the galaxy on the belt of Orion? Then you find out there's a cat called
Orion.
Orion.
And it's got a collar.
It's got a collar with a pendant, and in the pendant is a galaxy. We know because the laws of physics don't scale relative to other laws of physics.
That's not going to be.
You're not going to get a galaxy inside of a marble sitting on the necklace of a cat any more than you can have an ant the size of a house crawling out of a cave.
Right.
The forces don't allow that. Nor do they allow you to be too large.
Okay.
So could there be life the size of a galaxy? If you're the size of a galaxy, let's say our galaxy, which is 100,000 light years across.
Right.
All right. And there you are. So your limbs and everything occupy this volume. And now your head itches. How long long will it take you to scratch your head? The signal has to get to the thing that's going to do the scratching.
So even at the speed of light, if your arm is halfway across the galaxy,
Right.
that is 50,000 years just to get the thought down there.
Right.
And then another 50,000 years to pull it up here.
And scratch.
Right.
And so large life forms never itch. Okay. But
there you go.
Still, what we know of life is that it does a lot of evolution does a lot of experimenting. And so it needs to see, oh, this doesn't work. Let's try this. That works better. Oh, here's something that works even better. Oh, this is bad. We can't help this. You go extinct. All right. There are these experiments that have to happen on a time scale within the age of the universe. If every new thing that you're going to try as life takes hundreds of thousands of years just to experiment on, how are you going to have the biodiversity that we think of as a natural feature of what life is and puts forth? So, above a certain size, we don't see that as realistic or reasonable. Lessons in size and life.
That's nice.
It's a fascinating field that brings together physicists and biologists.
My question is related to the edge of the observable universe. What observations have been made, and can you describe what it looks like? I have heard that there appears to be some type of haze. Is this true? And can you tell us more about it?
It's a purple haze.
Ooh. Oh, man. We writing songs right now. I like it.
So, a couple of things.
Talk to me.
The age of the universe is in our way.
The age.
Yeah. So there's a horizon beyond which we cannot see because the universe isn't old enough for light from objects beyond that horizon to have reached us yet. That's the horizon. It's not completely different from the horizon at sea, where you're at a ship and you see the horizon. Are you saying to yourself, is that the edge of the universe? No, there's probably ocean beyond that.
Right.
And if you sort of sail towards it, more ocean comes into view and you bring your horizon with you.
Yeah.
That's kind of the horizon is not an absolute thing.
That's true.
It's relative to you, and you are in the center of your own horizon. The exact center. Okay. Now, it turns out, as we look out into the universe, we see the universe younger and younger and younger and younger until we see it just shortly after the Big Bang itself. So technically, that's not quite a horizon. It's a time horizon more than it is a space horizon, because you can't see before the Big Bang. And so if you wait a few billion more years, as the universe continues to expand, then there'll be a place, a space horizon beyond which you cannot see. And if you travel that direction, again, you can take your horizon with you. Wow. So the real question is, do we really know how big the actual universe is?
Right.
Do you know how big the actual ocean is? Not really.
No.
Unless you keep sailing until you hit land.
That's right.
But if you're in the middle of the Pacific, that's a lot of sailing.
You have no
idea. So generally, when we speak of the universe, it's how big is the observable universe?
Yeah.
We got to contain it, because what's beyond that, we don't know. No reason to think it's completely different. No reason to think just beyond your horizon, there's something very different from the water that you're witnessing up until the horizon. No reason to think that. So too with the universe. Beyond an observable horizon, no reason to think the rest of the universe is fundamentally different from what's within our own horizon. And so, by the way, everyone sees themselves as the center of the universe.
That's true. That's true.
Which means there is no center of the universe.
Yeah.
And one of my most retweeted tweets, I guess it's X now, it was very simple. I said, because the universe has no center, it means you can't be it.
Now I'm disappointed. Now I'm very disappointed. Because I always thought I was the center of the universe. But you know what? I got to add one more thing.
What's that? Okay.
And what's so crazy is looking at how endless it is out there. I often wondered, is it as endless in here? Meaning, is there an end as you go inside as
the
well?
mind? Inside the atom?
This atom.
Okay, for a while there,
Wow.
people suspected, because they wanted it to be true, that you see the sun and you see planets orbiting the sun.
Yeah, it's
when we first
are we an atom?
Exactly. So when we first cracked the atom, they said, wait a minute, there are electrons going around the nucleus. So we borrowed the same vocabulary.
Yep.
We don't call them orbits, but we call them orbitals.
Yep.
Okay, same idea,
Yep.
right? It's something, and they said, well, if that's what it is, what happens if we go into the nucleus of the atom? Will it be that again? And then that again? Is it that all the way down? No, it's not. It's just not. There's atoms, and then there's us and this universe. And, not to get too pop culture on you, but in Men in Black, there was the galaxy on the belt of Orion. I don't know if you remember that.
I don't
Orion
remember.
was a cat, and it had a neck
Yes,
thing.
I
And in
remember
there
that.
was this sort of transparent
Yes.
ball, and inside that ball was the entire universe that we are living in.
Yeah.
And it's just this little dangly thing on the neck of a cat. Yeah. It's fun to think that and write stories about it, but it doesn't look like that's the case. Because different laws of physics apply to the large-scale universe than the small. And if it was the same thing all the way down, you'd see repeated.
That's true.
I think.
The rules don't stay the same.
They don't stay the same. They're
Got it.
very different. Very, very different. We don't know how to make galaxies.
That's right. This is
Failure.
where we are right now.
Yeah.
Right. The basics of like the time when the Big Bang up to the time that matter and energy separates, right? That's 380,000 years or so.
Right.
That's still secure.
That's
There's
still secure.
nothing that's challenging that. So the work that Cobb and Turner did in the early universe book, even decades ago, still applies. It's that part that comes forward that makes it difficult.
At which, for a while, we call the Dark Ages, right? So no stars are yet made. The universe has to expand and cool enough for matter to coalesce and make stuff.
That's right. That's right.
Okay, so are we making stuff sooner than that understanding allowed?
One of the big points is now our realization that for these galaxies to have formed, we cannot form stars the way we thought they did, and then let the stars age, and then have the stars form black holes, and then have galaxies gather around those black holes as they grow.
So are we still requiring that the black hole forms first, or that it can be made later? Why are we hinged to the black hole? I don't see the point of that.
The chicken egg problem, right, has been going on for a couple dozen years now.
Okay.
And the main issue is, how do you gather all the material that forms your galaxy if you don't have something to nucleate all that material around
So
those stars?
making galaxies was an entire cottage industry.
That's right.
And it has been, and it continues to be. But we need a rethinking of that early universe.
There is additional evidence that supermassive black holes must have existed before super stars that could create black holes, that could grow into supermassive black holes, could exist. The timing is starting to get really weird. The circularity of the arguments.
And by the way, here's something that's underappreciated, I think. The JWST was conceived for this very purpose.
Yes, absolutely.
We don't really know how you make galaxies. Let's get a telescope to help us. So it might have just affirmed what we thought was already true.
That's right.
But anytime you turn on a big telescope, bigger than anything that came before, seeing in windows you never saw before,
That's right.
you're going to discover stuff that nobody
You find
ordered.
new things.
Yeah.
That's right. And then you bring on existing technologies such as ALMA to come and confirm those things. It's not just a single isolated discovery.
Oh, yeah,
like
you
a-
can't
a
in
big
science. There's
thing.
no such...
That's
yeah,
right.
Yeah.
How often do you get the question, how do we know this is true, right? And the way I answer my students when they ask me the same question, I wind up saying, we know because of all the evidence that is stacked up against it, and then the inability to disprove it.
Yeah.
All right, even though we have tried. And so whether or not a thing is true in science, it's not a certain somebody from on high told you it is so, but rather we have to build that reality.
Yeah, and that's I use the phrase, it's an objective truth. It's been objectively established by measurements and observations repeated. So it shows we're onto something.
Yeah.
And we have a real piece of data there.
That's right.
And so you can't dance your way around that. Had it just been one observation,
Would not have been enough.
would not have been enough, and it would not have jostled the theorists from their perch.
I think that's right.
Yeah.
He says, I've always wondered if there are higher dimensions. Could the expansion of the universe be caused by space-time falling into another dimension? Like if our 3D space was a waterfall falling into a higher dimension and we simply perceive it as expanding in all directions. What would it mean for dark energy?
Man.
Interesting.
Damn.
First of all, let me just tell you, I do not know what kind of you are smoking in Croatia.
Stop.
But that is, please.
Send some here.
Yes, send us some of that Croatian over here. Go ahead. What a weird concept of our space-time
so here's the thing.
falling into another dimension.
Right. There's no evidence that one dimension is susceptible to another dimension in that way.
Correct.
So,
I
for
see what you're
example,
saying.
let's take the surface of a table.
Right.
How many dimensions is that?
That's 2.
2. It just has a length and a width.
Right.
No depth.
No depth.
And then I have another surface of a table. So I can make that table infinite, right?
Correct.
Now I can have another table that's separated from it that's also infinite.
And they're just running parallel.
They're just running And they're not. There's no one.
Yeah, there's no interaction,
and it's in a
nothing.
third dimension. And there's no. I can embed a two-dimensional surface in 3 dimensions, and it'll just sit there as 2 dimensions.
As 2 dimensions.
It-
inside of a 3-dimensional
Inside of a 3-dimensional
medium.
In our world, we have quantum physics where a lot of mysterious things happen. It's not mathematically mysterious, it's just intellectually mysterious. Particles pop in and out of existence.
Right.
Matter and energy are equivalent.
Particles behaving the same way over a large
They're
period.
entangled. You know,
Right.
there's weirdness that's going on. We can describe it mathematically. Is that weirdness completely normal in a higher dimension? Let's just ask for that. So what would be an example? Let's go back to our 2D world. Okay? And we're there, we're walking around, or slithering around, however
yeah.
2D people get around.
We're line drawing.
Yeah, we are only our perimeters to each
Right.
other. Right. Suppose we're looking around and we see a dot.
Right.
It just came out of nowhere.
Yes.
It's like particles popping into existence. It's a dot. Where'd that come from? I don't know.
Right.
And then we keep watching. We study it. We're scientists. We study it. And the dot becomes a circle. And the circle grows. And we say, and we're studying it, we're making measurements, and it grows to like a maximum point, and then it starts shrinking back. And it gets smaller and smaller. Then it's a dot, and it disappears.
Wow.
We be coming up with all kinds of theories.
Aliens.
Aliens.
Because we live in rural America, where the rural part of the paper.
City people. Rural.
We're in the rural part of the paper.
Of the two-dimensional.
Where the 2-dimensional, where the dot said I was out in the middle of the night. Dot showed up, got bigger and bigger. Okay, go ahead.
So we can't explain that. We
Right.
don't understand it.
Right.
And is it like the studying the elephant, but you don't see the whole elephant?
Yeah, okay.
You get 7 different descriptions: the trunk, the tusk,
Right.
the
The tail.
leg, the toenails,
Right.
the tail,
Right.
the side. None of those comport until you take a step back and say you're all describing the same creature. Okay, and that's the full understanding that no one gets at first. Do you know what I just described?
A hole.
No, I described a sphere
Passing through the paper.
The paper.
Because at one point it's just a dot because it's a single point
Yes.
of the sphere that's touching the two-dimensional plane.
Exactly.
But as you continue to move the sphere through, then what you have is more points in the 360-degree sphere that keep fanning out,
Yes.
but only in 2 dimensions, so they make a hole that keeps getting
They
bigger
make a
and bigger.
circle.
A circle. And then...
And how big does the circle get?
Whatever the size of the
The
diameter.
diameter of
and
the
then you
sphere.
come back, and
Right.
then you're down 1 point
And
again.
here we are mysteriously inventing forces and
Interesting.
phenomenon, and it's just a normal,
Wow.
it's just a normal sphere
Wow.
in the higher dimension of this example,
But
which
to
is
us,
3-dimensional.
But to us,
To 2-dimensional
in
people.
rural paper stand,
Paper stand.
in rural paper stand, that was a serious
It
phenomenon.
was a serious one. And they're reporting that to the government.
Right.
And people are trying to capture the next one.
Oh, wow, that's great.
So if higher dimensions pass through or
Right.
otherwise interact,
Right.
it can be very mysterious.
It could be right. Wow, dude, what a great question.
Yeah. So
okay.
so he was trying to account for the dark energy. I don't know what could be happening in a higher dimension to manifest in our dimensionality as dark energy. That could be a thing.
Right, it could be.
Yeah.
Yeah. Interesting.
Yeah, whatever dark matter is, we have no idea.
idea.
And maybe these guys will find it in their particle accelerator.
Right.
And if they do, we'd be very happy because right now it's just this term in our equations.
Right.
It's like
But we know it's something.
something's there.
Something's there.
And so we throw it in the equation.
Right.
And let somebody else figure out what the hell it is.
What the something is. What about dark energy though? Because that's not a particle.
Well, we don't know.
Harry,
Harry.
I'm going to throw this one over to you, Harry.
There was this original, one idea for what dark energy is what we call vacuum energy. So it's the energy left over in empty space once you've taken away everything else, all the atoms and all the particles. And in particle physics, the actual truth is that particles aren't really the fundamental ingredients of the universe. They're actually made of something more fundamental, which is called a quantum field. So for all of these 17 particles we talked about, there is a corresponding field, and the particles are actually like little vibrations in that field. They're like ripples in an ocean, if you like. So those fields, even when you've got rid of all the particles, they're still there in the vacuum. And if you the idea was that maybe dark energy is all the kind of quantum fluctuations that's left over in these fields in the vacuum. But if you run the numbers, you get an answer that is 10 to the power 120 times too big. So that's 10 with 120 zeros at the end, which is like a ludicrously enormous number. If it was that big, the universe would be ripped apart in an instant. So we have no idea what's going on really from a particle physics point of view.
So it's the biggest discrepancy ever
Right.
between a theory and an observation.
However, couldn't there also be something else, since we don't know what that is? Couldn't there be something else that's tamping the field so that it isn't ripping?
Now you're just making stuff up.
I mean, that's just as feasible as a field. wield.
I mean, no, you're dead right. Like this is what theorists do. They go, okay, well, this number's crazy, so let's add in another thing that cancels it out. That's exactly what people try to do. So you could be a theoretical particle physicist.
This is just perhaps semantics, but of your 16 particles plus the Higgs boson and minus the 3 force carriers, so that takes us down to 13, I think. Do you count their antimatter versions of those particles as separate particles?
Yeah, I mean, you can multiply that number many times. So like the quarks, for example, the version of electric charge for the strong force is called color. And whereas with electric charge, there's only one type of electric charge, in the strong force, there are 3. They're called red, green, and blue. So you get red quarks, green quarks, and blue quarks, bizarrely. So that means actually there aren't 6 quarks, there are 18. If you add in the antiquarks, that gives you 36. So you can go up to like crazy numbers if you take all these things into account. But basically the antiparticles, they exist in the same field. So you have your electron field. An electron or an anti-electron are just different sorts of vibrations, but in the same field. So we tend to just count that as like one thing, not 2. And because if you start doing that, it gets mad.
Okay.
Interesting.
Clarify that.
How are you able to manipulate our senses? These, in the end, are our first line of defense for survival. We hear, we see, we smell.
And taste and
And
touch.
we're so easily fooled.
Well, you're saying if we're so easily fooled, how did we last this long
Exactly.
as a species?
Yeah.
Well, again, it's because illusions are useful. There's this misunderstanding that illusions are something that we should try to get rid of. But in fact, illusions make us faster and more able to
You got to explain to
survive.
me how not seeing reality as it is somehow to our survival benefit.
Well, for one, seeing reality exactly as it is, we don't have the neural machinery that can do that. We just don't have the hardware or the software that would be necessary. The computing power would be disastrous. And so metabolically, and just think about reaction times, we don't need to see reality as it is. We need to see reality as close enough so we can make it out alive.
Interesting, because we can't see the flapping of the wings of a hummingbird. But if we did, that would require much more processing power in our brain and in our eyes.
So we need upgrade.
But I guess that was not important to our survival.
Exactly. You don't. Maybe if you're a hummingbird, that would be important to your survival to see another hummingbird.
See, we've created our own simulation in a certain sense.
Don't say that. That's
Why not?
scary.
I know, but
You're
that's,
scaring me.
what, cross the road.
You're saying our version of reality is our own simulation.
It is a construct. You're
Construct,
absolutely
that's
correct.
the better word.
Yeah, well, I like the word simulation too.
Yes.
And that because we're making it up. We construct more than reconstruct. We take little bits and pieces of the information that comes in and we make up a whole lot of the rest. So we do create a grand simulation.
Put it that way, it makes me wonder, we get bits and pieces of reality that if they don't otherwise make sense, we try to make sense out of it. And the sense making can be fraught with all kinds of error.
The brain is a storyteller. We tell ourselves stories about what's happening. It may have nothing to do with reality. And magic is a great example of connecting cause and effect in a way that is not true.